Capacitor characteristics. So we have seen kind of in many kind of videos that we have talked about the capacitor characteristics. So capacitor is a kind of or we can say it's a device that stores charge. So if it stores charge, then initially capacitor is discharged, and then if I apply voltage across the capacitor, it will start storing the charge, and one time will happen when it is full, and beyond that it won't allow the current to flow. Okay. Electronics is a science of resistance. So if I apply voltage across 2 points in a circuit, then it will look at the easiest path through which it can flow. Okay, means the current can flow. So if two end has a voltage difference, then it will tend to flow a current from a battery's one end to another end. It will take a path, okay, that has less resistance. So if I see, so it's a kind of inevitable, means it's natural to talk about any device in terms of resistance. So if I have a capacitor and it is connected to a circuit, then initial resistance of the capacitor is zero. If there is no charge, it doesn't offer any resistance. So if I apply voltage across it, then sharp current would kind of flow through it. But once charge getting started, when one charge gets started storing into the capacitor, its resistance is changing. And from 0 to, once a kind of current is flowing, okay, one time will come, so resistance will grow, and one time will come when resistance will be infinite. At that point, since it is infinite, so either the circuit voltage, so it has to take another path, or if this is the only path, then current cannot flow. Okay, so that is the science of science in electronics and capacitor. Now, can I miss capacitor characteristics we have seen? Very nice. Means we saw the charging time, and then we saw also that it discharges. Where capacitor can be used, where a variable resistance can be used, rather we can say this. So, can we use capacitor in a circuit? How? Means I can, if I place in a circuit, then it will charge. Okay? If I remove the voltage source, it will discharge. Can we think about charging and discharging in different paths? Capacitor would charge from a path, and capacitor would discharge from another path. Okay, so when capacitor is kind of its resistance is zero, and it is connected to battery would kind of source it, and it would fulfill. And when it is fulfilled and connected through the battery, then it will be kept fulfilled. Okay, but if it gets disconnected from the battery some, then it should be able to discharge from the other path. If I can kind of find this kind of charging and discharging, charging and discharging. Okay, so we can kind of find a way to get oscillator. If capacitor is charging, it is discharging, charging, discharging, charging, discharging. Okay, so it is kind of, it will give a wave, okay, electromagnetic wave, where if it is too quick and where there will be kind of a voltage, voltage, no voltage, voltage, no voltage, voltage is growing, coming to zero, growing, coming to zero, a current is growing, coming to zero, growing, coming to zero. So, can we use capacitor as an oscillator. So we'll see that how we can use a capacitor as an oscillator if we provide different paths for the charging and different path for the discharge. So that will get further discussion on capacitor as an oscillator. So we'll see what we are trying to achieve. Okay, so this is a typical kind of diagram of rain LR. Okay, so we have taken it as an oscillator. Okay, now we'll see that what is the circuit actually. So this is NPN transistor and this is PNP transistor. So being PNP transistor, so this is the direction of the arrow of the, so this is emitter, this is collector and this is base, and similarly arrow sign, this is emitter, collector and this is base. So transistor is nothing but it's a kind of a dual junction diode. Okay, it's not a double diode, but it's a dual junction diode. Okay, so in capacitor, in transistor, this is one junction of the diode, this is another. So it's a kind of a straight diode. It's not like the way it is drawn. So two junction, one junction is base and collector junction, and one junction is base and emitter junction. So if base and emitter junction is in forward bias, in kind of active region, okay, and this is in reverse bias, then this transistor is said to be in active state, on state. Okay, so similar condition here. Okay, so this is P and this is N. So voltage at here is more and here it is less. So this would be forward bias and okay. Okay, and this is N and this is P. So at N the voltage is higher and P voltage is low. So this should be considered in reverse bias. Okay, so this is a typical kind of NPN and PNP circuit. Now from base 330 kilo ohm resistor is connected to 3 volt and 10 kilo ohm from base connected to the ground, straightforward. Okay, now in between we have collected 0.01 microfarad capacitor and 8 ohm speaker. So 8 ohm is the resistance and then this is the capacitor and this is, so if I remove this capacitor and remove this speaker, then the collector is directly connected to sink and base after 10K it is directly connected to sink. So this transistor dual would be considered as in active state. Okay, so it would be conducting kind of signal, electrical signal. Okay, now if I connect this circuit, okay, if I think that there is a switch and I connect this circuit, so as per the characteristics of diode, so a charge would start accumulating in the diode, in the capacitor. Okay, so at the beginning when capacitor is discharged, this would behave as a short circuit. Okay, so at the beginning there is no capacitor. That means it's a pure short circuit. If it is a pure short circuit, so there will be current flowing through it. Okay, and speaker is receiving the current. After some time, when capacitor is charged, okay, so after some time when capacitor is charged, it is behaving like an open circuit. Means its resistance is infinite. If it is open circuit, current cannot flow it. So these two transistors will become open, means they are not active. I mean there is no current through the speaker at all. So when capacitor, so there are two, can we see now? So I can add now in our scenario, if we see, okay, so when transistor is active and when at the beginning the current is flowing through the capacitor, it is storing the charge. So slowly it will kind of obstruct the current, and one time happen it will be open. So at the beginning it will kind of shunt it and current would flow through the speaker and there will be noise in the speaker. And okay, so after that, once capacitor is charged, then it is disconnected and there is no current. Okay, so current can flow through the PNP transistor, but it is not in active state because it is kind of dangling and there is no current. Okay, now there is another scenario. Okay, so this would be considered as third scenario. Okay, so it is marked as green at the beginning, means it is passing the current, and when in open state it is marked as red, means capacitor is fully charged. When capacitor is fully charged, okay, this is 10K resistance and there is, okay, so this is a diode, okay, so when capacitor is fully charged, it is seeing this as a path to discharge. Capacitor is charged from this path. This is the voltage source. If this is the voltage source, current is flowing from here and capacitor is charged. When capacitor is charged, okay, then here 330 kilo ohm resistance is there and voltage source, so it cannot discharge through this path, but it is getting another path to discharge. Okay, and capacitor after some time, capacitor is discharged. If capacitor is discharged, okay, so if capacitor is discharged, okay, it will again behave like a short circuit. Okay, the moment its resistance, so discharge means its resistance is lowering, and one moment will come that it will be short circuit. The moment current starts flowing through it, then there will be again noise in the speaker. Okay, and once it is charged, when it is being charged, Okay, so once it is being charged, after some time it will become fully charged and it will make it as open circuit, and then again there is no current. So it would behave like a kind of current going up and there is no current, current going up and there is no current. So we can kind of think like, okay, so probably we can draw it here. Okay, so beginning there is a flow of current and then suddenly current comes to zero. It will remain as zero till capacitor is discharging. Then current will come up again and current will remain, okay, till capacitor is charging. Then current will go down and capacitor is discharging, and then current will come up. And so this is a kind of vague idea that this can be the kind of current coming, means voltage is developing there and not developing there. It can be means it is on and off, I can say. It can be exponential, this curve what we are saying. Okay, so if a speaker is receiving current and not receiving current, it will do tick 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 kind of that. So now in our actual lab, what we have done in the actual lab, so the capacitor value, okay, so I can kind of close it. Okay, probably it should go away. Okay, so now what is the actual scenario what we have taken in our lab session? Okay, so probably we can add a slide called lab, and then what we have done in the lab, that we'll see. Okay, so now we understood that capacitor is behaving like a variable resistance. Okay, so in lab session, what we'll see, so I have taken it as kind of 1 microfarad. Okay, it won't be that much high speed tick tick tick. Okay, otherwise 1 microfarad, and instead of 3 volt, I couldn't arrange it. So I got 2.7 volt, 2.6 volt, 2.59 volt rather, in actual sense. Okay, so this is what we'll see in the lab. Okay, so this is lab. Okay. Okay, so now what we are going to do now? Okay, so now we have a kind of a lab session, and in lab session, as discussed, we have kind of okay, so now we have taken 1 microfarad capacitor. So tick will not be that fast because charge and discharge will take time, and 2.59, but it works. Okay, and 8 ohm speaker is there, so that I could not arrange, so I have taken kind of one old mobile speaker, so that I have used. Otherwise it is 10K and it is 330K BC 547 NPN transistor and BC 557 as PNP transistor, so that we have taken. So now we'll see the variable resistance that is developed through the capacitor, and one is charging circuit. So charge comes through the battery source to the capacitor, and through this loop it would discharge. Okay, it will discharge to a level that it will connect again and it will charge. Okay, so once it connects while charging, so speaker would kind of, it will start speaking. So that is the idea. Okay, so that we'll see in the lab. Okay, so we have connected the circuit. So the voltage source is around 2.6 volt, and okay, so I think I'll show through this. Okay, so this is one resistor 330 kilo ohm, and there is one resistor here inside, and that is 10 kilo ohm, and the capacitor here we have taken 1 microfarad. So based upon the time constant, so that much it will take. So if I disconnect anything, so sound would go off. So if I disconnect the battery, okay, now if I connect the battery again, okay, so this is kind of oscillation we are able to generate. So capacitor is kind of charging and it is discharging in some time. So probably we can add a bigger capacitor to have the sound not so frequent, or lesser than this capacitor for the sound to be kind of more frequency. So that is the concept. So here what we see, this transistor is NPN and here this is PNP. So circuit is kind of connected the way it is shown in the diagram. Okay, so quickly I'll test the speaker. Okay, so if I disconnect anything, if I take out the capacitor, the sound would go away. Okay, so I'll connect the capacitor again. Okay, so quickly we will calculate the kind of its voltage. Okay, so I'll disconnect it. Okay, so okay, so it is around 2.6, 2.59 volt. Okay, so we'll proceed on capacitor based oscillator, and what we have seen till now is it works as a capacitor initially behave as short circuit and then open circuit. Okay, if we see the kind of charging curve, capacitor charges from the voltage source through this path. Okay, and then it discharges through this path. Okay, so capacitor charges from both paths, so I think that would be better explanation. Okay, so capacitor is kind of getting charge from this path also, because voltage from this path also. Okay, so it is getting charged from this path also. Okay, so voltage source, so this is kind of reverse bias, so the impedance would be high, and being this forward bias, so impedance would be less. So it is getting charged from both directions, and when capacitor is charged and it has to discharge because the sink is in this direction. Okay, so this makes a loop and it would discharge, so making it forward bias, so discharge would be very quick. It's a 10 kilo ohm resistance, and here 330k and whatever the resistance this path is showing. So parallel we can kind of calculate, and plus 10k, so that much resistance it is getting when it is charging. So two paths are there, charging and discharge. Okay, so now we'll see kind of okay, so we'll see kind of the circuit from the close view. So that is the first idea. Okay, so I'll show the kind of circuit diagram. So it is oscillating. So from little closely how it is connected. Now we have a capacitor, and we can see there is a wire. So we'll kind of check it as if it is can behave as a rain alarm. So that we'll see. Okay, now we'll see kind of we'll simulate a rain alarm. So we'll have a rain alarm probe, and that will be connected from here. So we disconnect the circuit and connect a rain probe to wire, and we'll put in a kind of water, and we'll see it really oscillate. So kind of keeping 1 microfarad as a capacitor. So that we'll see. Okay, so this is the kind of circuit connected, and we can hear the oscillation sound. So now we have connected kind of 4.5 around 4.7 microfarad capacitor. So frequency is less. So those things we'll calculate later, and how much time it should take, and what is the value of resistance, and those things. Okay. Now, okay, so this is the speaker, this is the circuit, this is the battery, and battery voltage we have already shown, it is around 2.59 volt. So 330 kilo ohm resistance we have taken out from the base, and in between we have inserted one kind of a probe that we can see. Okay, so it is connected, so it is kind of oscillating. Now we will disconnect it, so we disconnect it, so there is no sound. Okay, so if I connect it again, there will be sound. Okay, now we'll see if it behaves as a kind of a rain alarm. So I have water to test. So I'll place inside the water and we see that if it really oscillates. So one probe went inside the water, another probe is going inside the water. Okay, so it behaves very well as a rain alarm. So if it kind of water is behaving like a conductor, and when they come in touch through water, so it starts oscillating. There is no change in frequency and there is no change in sound also. Okay, if I take out one probe out of the water, sound goes away. I place it again. Okay, if I take out both out, no sound, and if I connect it together, okay, so there is sound again. Disconnect, no sound. Okay, now whatever frequency we are generating, we are seeing, so those will analyze. So this is to kind of show that it behaves good as rain alarm. Okay, and if so if we see the circuit, then two transistors we have used. One is this transistor, another is this transistor. Two transistors are used. So this one is PNP and this is NPN. This is 330 kilo ohm and this is 10 kilo ohm and this is 4.7 microfarad. Okay, we'll measure what it is actually. So that will do that. Okay, so we have seen now rain alarm. Now it's time to go for kind of various other capacitors. So 1 microfarad we'll see, then 4.7 microfarad, 10 microfarad and 220 microfarad. So 220 microfarad, the charging time would be kind of very high because 220 microfarad comes as 0.22 millifarad, and then multiplied by the parallel circuit what we see charging curve from this direction and this direction. So that parallel will compute, but still it will be very high. Okay, so charging will be very high and discharging will be less, but still it will be very, because it is 220 microfarad. 10 will be quite less, 4.7 less, and so 4.7 and 1 microfarad means it will be really quicker, in the sense that charge discharge will be quite fast, whereas 10 microfarad it will be okay, and 220 will be pretty slow. So that we'll see now. Okay, so we'll see it is oscillating now. Okay, so we will, maybe I can place it near the speaker. Okay, so it is oscillating. Now we will measure the oscillation. So this is with 4.7 microfarad capacitor. Okay, so I'll take it out. Okay, now I'll put 1 microfarad capacitor. So frequency is high because 4.7 and 1 microfarad. Charge and discharge is quicker. So we can see the difference. change it to another picture. So I have one 10 microfarad capacitor. Okay, so first difference is that frequency is low, and second thing is that audio is not continuous. Earlier audio was continuous, now it is not continuous. Yes. Okay, so it taking time to charge the capacitor. Discharge is quicker, okay, because 10 kilo ohm resistance through which it is discharging, so it is quicker. But charging is 330 kilo ohm, and since it is a 10 microfarad capacitor, so that is kind of, it is means it is noticeable that it is taking time. Okay, so I'll connect the bigger 220 microfarad. Okay, so there is no oscillation. Okay, so there is no oscillation, or it is we are waiting if it is really oscillating after some. Okay, so there is oscillation, but we can see that time taking is very high. There was some two sounds are quicker, means that is when it is discharging. Now it will take long time. Okay, so it is clear that everywhere it is same. If I had connected a 10 microfarad capacitor, then two sounds were quicker, and then third was very long, then again quicker, then third. So charging and discharging happening through different resistance, and that much time gap we are seeing. Okay, so we have seen the kind of charging discharging for the 1 microfarad. So Audacity is a kind of audio editing tool, and there we have kind of taken the graph. So we can see it is 1.09 second and 1.21 second. So within 12 seconds, so 1 microfarad, how much charge discharge it takes. So one double line is kind of, so if gap is big, can we see? If gap is big, then this much time it takes to charge and discharge is smaller. So if I take one, how much charge it takes? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So probably within less than 4 seconds, 23 times it is charging and discharging. Whereas for the kind of 4.7, okay, so it starts from around 2.01. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 11. So within 9, 2.01, within 8 seconds, around 11 time it is charging. Okay, so that is, so more computation will do. Okay, now with the 10 microfarad and 220 microfarad. So with the 10 microfarad, we can see it starts the story from 1 minute 42 seconds. And then within 8 seconds, 1 minute 54, 3, 4, and 7. Within 8 seconds, kind of 7 times it oscillates. Okay, and Mr. 220, it takes a lot of time. So if I say that it starts at, okay, so it is around, I believe, 4 minute 37 seconds, and then 6 minute 30 seconds. So around 2 minutes it takes to oscillate 4 times. So it is quite slow. Okay, so now we will see that we have added in the circuit the collector of the PNP transistor. This is PNP transistor, is connected kind of near a speaker. So can we connect it to sink and let it charge and discharge through this base only? So that we will see. Okay, so here we will kind of connect the capacitor, the collector, okay, to sink, and then we will see how it is. Okay, so we are seeing the kind of heartbeat. So we'll see what is the scenario if I take out the collector, the PNP collector we have connected to the speaker, and if I connect it directly to the kind of sink, what will happen? Okay, so no sound. So if collector is connected to the sink directly, not to the speaker, there is no sound, because the speaker is kind of, it is charging and discharging through the emitter of the NPN, but it receives energy from the PNP transistor, and through that energy it is kind of oscillating. So I'll connect it back to the speaker. Okay, so collector must be connected to a speaker because the speaker receives a power from the collector and of the PNP, and that's why it is making the sound. That power is missing. Okay, so that power is missing if I connect directly, and now power is available. Okay, so that is energy of the collector. Now we will measure the kind of each resistance. Okay, I have brought a multimeter. Okay, so we can take it out. Okay, so we'll measure the resistance. I hope it is visible. Okay, so first we'll measure the 10 ohm. So it should be 10 ohm. Okay, so it is 10 kilo ohm resistance. Okay, this is one of another we'll measure. It is around 300 kilo ohm, 310. What we have seen so far in capacitor as oscillator, the theory part means if it happens, if capacitor nature is this, and if transistor is nothing but it is kind of dual diode, dual junction diode. It's not double diode, but it is dual junction diode, and if resistance kind of it generates a resistance when current flows. So then NPN transistor, PNP transistor fundamentals that we saw. Then we saw the working model, means it actually oscillates, and if it oscillates, it generates noise. Okay. Now it's time that we'll see kind of currents. So currents are crucial. If we see any typical NPN transistor or PNP transistor. So it's a dual junction diode. So two junctions. So typically when we want a transistor to be in active mode, so we keep kind of one junction in forward bias and one junction in reverse bias. So NPN transistor like BC 547 we have taken. So if we keep kind of a base emitter junction as forward bias and base collector as reverse bias, then we can use transistor in active mode, and if its base voltage kind of go beyond the 0.6 volt, this is what we are saying, but I have seen kind of its specification 547 BC, and it talks about 0.65 volt, but what we have seen, we are seeing 0.6 volt, so I have in front of me. So this is BC 547, and similar to this we have BC 557 as PNP transistor. So if a voltage goes above 0.6 volt, then means base voltage, then it starts kind of then a base emitter junction becomes kind of forward bias, and if become a forward bias diode, then it starts conducting electricity. So now we'll see in practical way that we talk about that voltage level at base, voltage level across the capacitor, it grows. So if voltage level develops, because it is accessing voltage from VCC, from the power, and this makes the base voltage come up, and where base voltage, if it is crossing the kind of the threshold, after which it will become conducting active, then NPN transistor become active. If NPN transistor become active, then it makes PNP transistor become, means this is how it is connected. Okay, and transistor is on. If transistor is on, then capacitor kind of it finds a path. Earlier transistor was switched off, so capacitor has only one path, that to be charged from the voltage source. Now, if capacitor, when a transistor is on, capacitor gets chance to kind of get, there is another path. Now there are two paths. One path is from VCC, that voltage is coming, and another path is from base to emitter. So that path, capacitor start discharging, unfortunately. If capacitor start discharging, transistor base will be at one level because it has inertia, so it will be active. But if capacitor goes beyond a point in discharging, then transistor will become inactive immediately. Okay, so transistor is behaving like a switch. It will be active for certain duration and it will go off. So capacitor behaves like either it charges from the battery or it behaves like a power source, where it is discharging through base emitter diode junction, but it keeps the transistor circuit active also because it has voltage, but it has limitation. When it discharges more, then everything goes switch off. Then it starts charging. So when it is switch off, the path toward the transistor for the capacitor is dead. There is no path there. It starts charging again. So we have used 10 kilo ohm resistance in series with the kind of capacitor to the base, and from base to voltage source it is 330 kilo ohm resistance. So those characteristics we'll see. Now we'll also see that the sound that comes from the capacitor, that sound is not the current sound. That sound is kind of a transition sound. Okay, so if transition happens, current in the transistor circuit, if suddenly transistor circuit becomes active, then there will be kind of big flow of current through the speaker in kind of 200 milliampere, that way. So sudden flow of current, 0 to sudden flow, it will spark. It will speak, tick. Then from that much high level, suddenly if it drops, then it will make tick. Okay, so two tick we hear, and that two tick, it keeps repeating. So that's what. Now, in the practical way, we'll see how much current flowing through the through speaker, how much current flows through the collector of the transistor PNP, how much current flows through the emitter of the NPN, base of the NPN, and through the capacitor, charging, discharging, everything. So then we'll try to kind of stick to kind of the voltage relationship in capacitor at particular time, what is the voltage and its exponential form of equation. That anyway we have done in the past in the tutorial. So that we'll use and we'll kind of try to verify. Means the idea is if transistor is taking this much time to discharge, because the capacitor is not getting charged fully. The full voltage source what we see is higher, but capacitor will come to a stage. So we don't know. Means capacitor from zero, it come to a stage till transistor circuit becomes active. It has to come to this stage. As soon as it becomes active, then capacitor will start discharging. As soon as it comes to a level, it is not zero. It comes to a level where transistor will become inactive, then it will start charging again. To a level where transistor will become active. So it will never come to a stage where it will get the full energy from the battery. Okay, so that calculation would be kind of difficult, and I don't know how much practical it is. But what I believe is the capacitor charging and discharging. So what I believe is the capacitor charging and discharging, that is kind of logarithmic or exponential, whatever the equation is. So time should be same. So if I charge a capacitor, then it charges immediately. Then slowly it becomes slow. At the end it will become very slow. If I discharge it, it will discharge immediately. And slowly it will become very slow. So if I calculate the kind of discharging time, then through that we'll try to manipulate something and we'll see that how much it is practical. It may go beyond what we are doing. Means we have to go with the kind of a transistor resistance, capacitor resistance we have to calculate practically, how much it is changing and like that. So that should be done. Okay, so that we'll see now. Okay, so we have kind of, as we stated, we have finished the kind of showing the output. Now it's time that first we'll measure the components, and once we finish the measuring the components, then we'll start kind of measuring the current. Okay, so before we proceed, first we'll make it sure that it is working. Okay, so it is working. Probably it is kind of 4.7 microfarad capacity. Okay, now we will measure the resistance of speaker. First step. Okay, so it is 8.5 ohms speaker is. Okay, so I am trying to calculate voltage of the battery. So we are using different battery. So it is coming around 3.69 volt. So this is the kind of a new battery we are using, and it comes to this much. Okay, so we are done with the kind of measuring the component. Now we will measure kind of voltage across capacitor and voltage and current across capacitor, voltage and current across the speaker, and then emitter current, collector current, okay, base current and base voltage. Then we can kind of interpolate the others that can also be calculated. Okay, so what we'll do now? Okay, so this is, if we see, then this is IB. This is IB. This is IE. This is IC. Okay, so IC of the PNP. Okay, so, and we call it kind of, this is both way. So this is, we'll say I capacitor. Okay, that will measure. So we'll measure IB. And here the voltage would be VB. Okay, this is IE and this is IC. Okay, so PNP, and we can call it as I capacitor. Okay, so these things will measure, and then we'll see kind of how whatever we have kind of seen in the theory part, so it actually kind of corroborate. So that is the idea. Okay, so that we'll see now. Okay, so we'll proceed on the demonstration. So circuit is connected. So what I'll do is kind of, I'll connect a 4.7 microfarad capacitor, and first I'll show that it is working. Then we'll proceed with the measurement. Okay, so it is working. It is in working condition. Now I have taken kind of one 750. It is written 1000 microfarad, but we have already calculated in another tutorial that it is 750 microfarad actually. So if that is the case, then the operation should be slow. So if it is slow, then we can measure kind of calculations more neatly. So first I will calculate the IE. So in the NPN transistor, whatever the current is flowing, so that I will calculate. Okay, so now it should kind of oscillate first of all. It will take little time charging and discharging. So probably it is charging now. Okay, so we heard one sound. Okay, so two sounds we can hear, charging and discharging. So now I will measure the IE. What is the emitter current? So that is one of the crucial thing. So I can kind of disconnect it and we'll calculate. So this is the wire that is coming from emitter. So I'll just kind of make it round with ammeter. So we will have an ammeter. Okay, so now, okay, so I have placed at ammeter, and so this is one side, and another side of ammeter is already connected. So it should show reading. So it should oscillate, and it should show the reading. Okay, so first sound we heard. Now capacitor is charging. So when it is charging, there is no current in IE. Once it is charged, and when it is active, at that time the IE will be around 2 milliampere, and then when then capacitor will get a chance to kind of discharge on that path, and it will start reducing. Okay, so the region what we saw now, so that is kind of active region of the transistor, but since capacitor is discharging, so at one moment it will cut off. So now it is cut off, and capacitor is charging. So this is IE, and IE reaches 2.22 milliampere. This is what we have seen. It takes around 30 seconds to charge and 4 seconds to discharge. So it is charged, discharging, discharge. So transistor is becoming active and passive, cut off in during this phase. We'll kind of quickly we'll measure the collector current of the PNP transistor. So I'll connect it as this. Okay, so this is PNP collector, PNP collector. So that current will measure. So okay, we have connected the ammeter, and ammeter will be connected here. This is okay. Ammeter will be connected at speaker end. So this will circuit is complete. Okay, now we can see the. So capacitor is charging. Around 130 milliampere current is flowing through IC of the collector of the PNP. So that much is required to make the speaker make sound. So now capacitor is charging. Okay, around 130 milliampere current is we can see. So then it is started discharging, and IC is decreasing. At one moment transistor circuit will be cut off. So capacitor is charging again. So this is IE, NPN and IC. So both we saw. 127 it goes, and around 102 milliampere transistor goes cut off. So up to from 127 to 103, I think that period capacitor is discharging, and beyond a limit capacitor is kind of then it is switched off. So next we will measure IB, then we will measure current in the capacitor. So capacitor one end we can take out. So we'll reconnect it the way it was. Okay, so it was like this. So collector was connected here at the speaker end. Okay, now we'll see the current flow in the capacitor. So capacitor one end will connect to ammeter again. Okay, this is how it is. Okay, so we have taken out the capacitor and we will measure current. So first it should oscillate. Okay, so it is first of all it is oscillating. Okay, now it's time for capacitor current measurement. So current, we can see current is decreasing, means it is charging. So capacitor is charging. So right now it is 10 microampere current is there. Capacitor is discharging. Okay. So now capacitor is charging. So when capacitor is charging at the initial phase, there will be maximum current, that is 11 microampere, and it will decrease. So it will come to 10 microampere. Then suddenly it will kind of start discharging in reverse. Now it is positive current. Okay, it reached minus 9 volt. So 11 volt to 9 volt, 11 microampere when it started charging, and it reaches up to 9 microampere. Then it will go in negative, in the sense that capacitor current will be reversed. First it was charging, so current was kind of from battery to the capacitor. Now capacitor to the circuit, so it will be in minus. Okay, so it reaches minus, I think 30, we'll see again. Minus 90, minus 35. So when it starts charging, minus 90 microfarad, means 90 microfarad current starts from capacitor. So, and then around minus 30, it kind of goes before transistor is switched off. So now transistor is switched off. Minus 92 to 34, that much it goes. And while charging, at the beginning it will be high current, 11 microampere, and then it will go to 9 microampere before it starts discharging. Minus 92. Okay, so around minus 34, 32 it goes. Okay, now it's time to measure the VB. So we will kind of release it. Okay, so capacitor 750 microfarad capacitor. So we will connect it back. Probably we will kind of measure voltage across capacitor, then we'll measure the VB of the NPN transistor. So voltage across the capacitor, if we want to measure, then we'll put in voltage mode. Okay, and then this is negative, and now we will kind of take out and okay, so voltage across capacitor is changing. We can see now. So it is going up to 30.34 volt and decreasing, and it is going up to -6. Okay, it is charging. Charging, and it is going up to 0.3, 0.3435 volt, now discharging, and -0.06, then it is charging back. -0.06 means it is 0. Minus it is going because there is a voltage drop across the speaker, and since it is in other kind of polarity, so capacitor is going in negative. So it is kind of charging from other direction. Okay, so now it's time that we'll measure the VB, the voltage across much awaited. So we'll place this into sync mode, and here, so much awaited VB we will measure now. Okay, so we have connected a wire in the VB. So VB is VB is growing. .62 it reaches. So that is conduction mode and not discharging. Okay, voltage is growing. So capacitor is charging. Okay, so voltage at the kind of base of the NPN transistor, it reaches more than 0.6 volt and it remains there at that voltage, so that it will be active for some time, and then it becomes non-active and it drops. So now voltage is growing, so circuit is kind of cut off, capacitor is charging, and okay, so it remains there for some time. Okay, and when it falls, at that time capacitor was at was charged for some, so 0.11 it starts. So VB is in beyond 0.6 volt. It is showing in the conduction region, active region, and this is how it is. Okay, now next question is kind of can we measure? Okay, so we have measured emitter current. Okay, now we will measure a base current also. So base current would be kind of little tedious to measure. So we'll put in emitter mode and we'll take out this. Okay, if it is in base current mode, then we have to take out. Okay, so resistor would be now, both resistor we have to take out. Okay, and okay, so we have connected the base somewhere other place, and now we'll connect ammeter. Okay, through ammeter current would go. So ammeter is connected to base. First it should oscillate, and then we'll connect back the. Okay, it's working. So this is IV, base current of the NPN transistor. So base current is 0. There is 0.0. Okay, 1 micro. So there is no. It's transistor completely switched off. There is no current going in the transistor. One 19 microampere current goes and it comes down. Okay, so when it is active at that time, 119 microfarad, that much is the kind of current flows. At the beginning, current will be maximum. It will slow down as capacitor kind of discharges. Okay, I think ammeter is not kind of very nicely functional. It is oscillating too quickly. This is what we can see. Okay, so in kind of microampere range. $160 and 53. It oscillates between two kind of current range. Now we will kind of we'll measure the voltage across the speaker, how much voltage drop it is making, and then we'll wind up. So I think we understood how it is. Okay, so we have connected it again. Okay, we place in voltage mode and we'll measure the voltage across cap. First it should oscillate the way we have made the connection. Okay, so we have made the connection. It should oscillate. Oh, it's oscillating. So 1.4 volt it goes along the speaker and 0.1 volt. We'll wait and see more. .4 volt and 1.1 volt. So the voltage across capacitor along the speaker, it kind of oscillates from 1.4 volt to 1.1 volt. So that is primarily from the collector current from the PNP transistor. Okay, so the collector current in the NPN transistor and then emitter current in the PNP transistor. So those things can be kind of interpolated with the emitter current in the what we have calculated. Okay, so we'll bind up now. Okay, so we have seen kind of the output, the experimental output. Now we have kind of, so these are the readings. Now we'll collect this IC to the proper place. So this is just for sake we did. Okay, so we'll collect IC at that place. Okay, so we have kind of connected back the IC. So, okay, so this is the actual circuit and collector of the PNP is connected before kind of the speaker, and now we have measured IB, VB, current across the capacitor, IE and IC of the PNP and voltage across the speaker. Okay, so voltage across the speaker also we have measured. Voltage across the speaker. Okay, now we have all the graphs ready. So this is IE, that is NPN transistor, and these are the readings we found. And from the graph we can see like the IE. So this is when transistor comes in kind of conduction. Okay, so transition current comes in conduction while at the same time capacitor is discharging. So we can see I is falling. It came to conduction, I mean active region, the transistors, but the current, the emitter current is falling continuously, and capacitor is discharging to a level that it is switched off. And this period there is no current, okay, zero current, and then suddenly so this period capacitor is charging, and this period capacitor is discharging. So while capacitor is charging, transistor circuit is disconnected, means is zero, and then capacitor suddenly charged to a level that emitter transistor become active. So this is now same we have PNP IC. So we can see that current is 2000 around 2 milliampere. It reaches 2 milliampere, the IE. Now if we talk about the IC of the PNP, same story. When transistor become active, then it also become active, and the capacitor is charging, so IE is decreasing. So this is also decreasing, but it reaches around I believe 120 milliampere, the IC. Because of that, a speaker is working, that we have seen. Okay, now capacitor is discharging. So while transistor circuit is active, so capacitor is discharging the way we demonstrated. So first of all, capacitor is charging through this path. From the VCC it is charging, and when it is charging, it comes to a level where VB is kind of a 0.6, and this transistor becomes active. Okay, and when it becomes active, at that time this junction, the diode junction, the resistance is very low, and capacitor is discharging. So it is a kind of a dilemma that circuit is becoming active, but at the same time capacitor is discharging through the base emitter diode junction. So current is decreasing, so transistor become active, but at the parallel capacitor is discharging. If capacitor is discharging at one level, capacitor is discharged and suddenly it falls. Means it can be seen. Okay, probably we will see in the VB. So this is how the story of IC. Now capacitor, so first let's see the VB, the most interesting thing. So when capacitor is charging, it comes to a level when VB is 4.4 somewhere, suddenly it comes to 6. This is the internal energy of the transistor. So this is the inertia or internal energy of the transistor. This is, we can see everywhere. This is the situation. Can we see this? So if voltage at the base of the emitter, it reaches to a level, then suddenly it picks up automatically. So from 4.4 to active, it picks up automatically. It remains active even though the capacitor is discharging. When it discharges to a level where transistor cannot hold its active condition, then suddenly it drops. Now capacitor is charging, so VB is again growing, and capacitor is charged to a level that it is 4.44. Again it picks up immediately. This is not capacitor phenomenon. This is a transistor phenomenon. If transistor base is coming to a level, it is picking up. Okay, so this portion is capacitor discharging and transistor is inactive, and this portion capacitor is kind of discharging and transistor circuit is active. Now we have seen IC. Now current across the capacitor. So capacitor current it drops, So from here we can see capacitor current. So capacitor is kind of when there is a negative current in the capacitor, minus 40, then it goes up to minus 90, then comes up to minus 40 and then 0. Okay. So negative current shows that capacitor is kind of in discharging mode. So capacitor is like capacitor is discharging, and from here it is charging. Okay. So we can say like from here to here, while it's kind of the discharging, the current is minus. Minus means capacitor has two type of current. One current is coming from the voltage source, and current is in this direction from top to bottom. And when capacitor discharging from bottom to top, the current, so it shows as negative. Okay, so capacitor is when it is charging, it is around 11 microampere, comes to 10, then comes to 9 microampere, and then suddenly capacitor, when transistor become active, suddenly capacitor starts discharging immediately. So this is the better curve. I think we should not demonstrate this. This is the beginning one. So then capacitor suddenly it reaches to minus 90 or something microfarad. Okay. Now capacitor is negative. Means capacitor is discharging. Capacitor is discharging to a level that transistor become active again. So transistor become dead again. So if we see the capacitor phenomenon, then capacitor is charging, okay, and right side, this area is completely dead when capacitor is charging. So while capacitor is charging, I can say that this area is dead. This is a very big thing. This area is dead. When capacitor is charging from this direction, the transistor circuit, so this, there is no current in IB and it is dead. So it is taking complete charge from the voltage source. Okay. When VB is kind of, when transistor is coming in active, okay, then now transistor is active, then capacitor is finding this path, unfortunately, to drain. Okay. Now capacitor is finding this charge path to drain, and it is draining to sink. Okay. So this path when taking, then at that time it is showing as negative. Okay. So capacitor, while capacitor is discharging, transistor circuit is active, and when transistor is active, okay, when we see VB, it holds at that position. Even though capacitor is discharging heavily, but it holds till it is active, and suddenly it is inactive. And this is what we are seeing in the capacitor also. So capacitor is kind of okay. So capacitor is in negative side, so it is discharging. Okay. Now it comes to a level where capacitor is discharged and transistor becomes switched off. When transistor becomes switched off, then capacitor starts charging again. It comes to this level and it is start charging. So when the capacitor is charging, at that time, at the beginning, the current will be high. Then slowly current will go down as it is charging. Okay. So this is the capacitor. Now if we see the IB, the current that is flowing inside the transistor. Okay. So IB he has like when transistor is inactive. Now when transistor become active, then IB comes to kind of 120 microfarad, I believe, and then IB is decreasing. while capacitor is discharging, IB is decreasing. And suddenly transistor becomes switched off and IB also becomes 0. So this phase capacitor is charging and then transistor becomes active and capacitor is discharging. Can we see this anomaly? Now capacitor is discharging, IB is decreasing. When capacitor is discharging, IE is decreasing. When capacitor is discharging, IC is decreasing. While capacitor is discharging, VB is not decreasing. Okay? It is at 0.62, 0.61 and 0.6. So it is like a flat. Capacitor is discharging all the while, but BB is not discharging. This is the internal energy of the transistor circuit. And when it feels that it is completely gone, then it is behaving like a switch. And then voltage completely drops. Okay. Then VB is charging, like when capacitor is charging. And then suddenly it comes up. Okay. When VB reaches 0.44 volt, 4.4 volt, as per its internal nature, it picks up to the active region. So this is something very interesting that should be seen. Okay, so we saw the I base. So transistor become active and then I base started losing the current. And as per the capacitor it discharging and then it becoming active. Now we'll see the most important, the voltage across the capacitor. So voltage across the capacitor is first we see that it is at high level voltage and then voltage drops. Okay, where transistor become active. So from this region to this region, transistor is active. When transistor is active, capacitor is discharging. Okay, now transistor is inactive, so it is finding a full path from the VCC to charge again, and this much it is charging capacitor. It reaches to a level when transistor become active and it is discharging. Now if we see the time instance, when it is kind of when it starts the discharging and when it starts the charging, okay, so okay, we have measured the voltage across the speaker also, that we can see that it is reaching 1.3 volt. But anyway, now if we see the calculation of the capacitor, though voltage across the capacitor is at any moment it is Vs1 minus e to the power t by Cr. So if I go ahead, then time it takes to charge the capacitor is minus Cr ln 1 minus Vt by Vs. Okay, we use Python code. So now 75.75 is the capacitor. I have taken full 330 kilo ohm and 10 kilo ohm while charging, and then if I do the computation, it comes around 25.33 seconds. So that much it should take. Okay, so that much kind of it should take. Okay, I mean I think it should be opposite. Okay, so this is experimental, what we saw, and this is theory. So with theory it should take around 25.33 seconds to charge, but generally it takes around 29 seconds. So I believe it's okay. 10% error in capacitor and resistance value, I believe it's okay. While discharging, we cannot, experimentally it takes around 5.2 seconds, but we cannot go with the conclusion, because if you see the capacitor voltage, okay, so capacitor voltage it is not showing here, but it reaches minus. So capacitor voltage reaches minus means, okay, capacitor, not capacitor current, capacitor voltage reaches minus. This proves that if capacitor is discharging, okay, and while discharging capacitor is reaching minus, this proves that there is still some voltage level here. Voltage level here means IC is there. So transistor has not gone kind of completely switched off, and there is a current in IC, so voltage drop is there. If voltage drop is there, and there is no voltage coming from this side disconnect, capacitor would start charging from opposite side. So that is the problem. It has no practical polarity. So that's why if we see the capacitor voltage, then it is reaching in the minus side. So if there are voltage and those kind of things, so I think it's okay. It means we should omit this. We should leave this capacitor discharging time. Okay, so this is how it is. So we saw that capacitor charges from VCC, and when it comes to a level, then transistor become active. As soon as transistor become active, this path is over because this has low resistance, and capacitor starts discharging while transistor is active. So active and discharging both are happening at the same time. Okay, now when both are happening at the same time, transistor become active, but it is losing the current, IE, IC of the PNP all. Okay, and at that time capacitor, when transistor is active, capacitor is flowing in negative direction, current means it is other way, then it is charging, and I base is also losing the current, IE, IC, I base all are losing the current because capacitor is discharging, but VB is not losing. It is standing at one location and it is completely going down instantly, behaving like a switch. Okay, and then capacitor kind of at the time it is discharging. When capacitor is discharged completely, transistor becomes switched off. When transistor becomes switched off, so this path to the right side, it is kind of infinite resistance and capacitor starts charging again. So this keeps happening. So when we see kind of the sound on the speaker, because voltage current here is reversing. So if we see the voltage level at the speaker, so voltage level at the speaker, if there is a sharp change in the voltage of current, then it will make a tick. If there is a sharp change, there is no sharp change. If there is a sharp change here, it will make a tick. Then, okay, then there is a sharp change here, it will make a tick. So wherever it feels the sharp change, it will make a tick. So when transistor is becoming active, it make a tick. And when transistor is becoming inactive, it makes a tick. So that is the kind of a story of the speaker. Okay, we can kind of go with audacity also to see actually the waveforms. It will take some time to kind of load it. Okay, so it is almost done. So we can see the spikes when it oscillates. Okay, so if I kind of, can we see this? So when it oscillates, there is a spike. Okay, so it is oscillating, it is making noise. So there are spikes that we can see. So this spike confirms that it is oscillating. See, we can see the spikes. So these are the spikes that we get in oscillating when it makes. So it is a kind of sharp noise it makes at that time.